solve second, we know that, or we have modulus of e raised to minus x sin x is less than or equal to mod of e raised to minus x. Since modulus of sin x is less than or equal to 1. Okay. Here let f of x is equal to e raised to minus sin x, which is equal to 1 upon e raised to x, and g of x is equal to what? E raised to minus x sin x. Okay. Here we have g of x is less than or equal to f of x. Okay. No need to write down it. If this integral converges absolutely, then integral g of x converges absolutely. Okay. So our aim is to show that integral f of x dx converges absolutely. Integration from a to infinity f of x dx is equal to modulus of integration from a to infinity modulus of 1 upon e raised to x dx, which is equal to integration from a to infinity 1 upon e raised to x dx. Modulus of this is 1 upon e raised to x. This is nothing but integration from a to infinity e raised to minus x dx. Okay. In previous video, we have seen one note that here alpha is equals to 1, which is greater than 0. Therefore, here alpha is equals to 1, which is greater than 0. So integration from a to infinity e raised to minus x dx is convergent. But integration from a to infinity e raised to minus x dx is convergent since alpha is equals to 1, which is greater than 0. Okay. That is this integral is convergent means what? Integration from a to infinity mod f of x dx is convergent. This mod is convergent means what? Integration from a to infinity f of x dx converges absolutely. Okay. So here we get integral f of x dx converges absolutely, and g of x is less than or equal to f of x. Therefore, by lemma we get integration from a to infinity g of x dx converges absolutely. Okay. Now we will see integral test for convergence. Integral test for convergence. Integral test for convergence. We will see integral test of convergence of series. Okay. Theorem. Let f be a non-increasing. Let f be a non-increasing function on closed at 1, open at infinity, such that f of x is greater than or equal to 0 for 1 is less than or equal to x is strictly less than infinity. Then series n runs from 1 to infinity, f of n will converge if integration from 1 to infinity f of x dx converges and series n runs from 1 to infinity f of n will diverges if integration from 1 to infinity f of x dx diverges. Here students, this is very important test. Let f be a non-increasing function on this interval such that f of x is greater than or equal to 0 for 1 is less than or equal to x is strictly less than infinity. Then summation n runs from infinity f of n will converge if integration from 1 to infinity f of x dx converges and summation n runs from 1 to infinity f of n will diverges if integration from 1 to infinity f of x dx diverges. Okay. Students, here note that the integral test neither says anything about the sum of the series nor it asserts that the sum of the series is the value of the integral. It is only a comparison test. Means if series f of n will converge if this integral is convergent, series f of n will divergent if this integral is divergent. It gives only comparison. Okay. Let us write down one corollary. If f of x is greater than or equal to 0 if 1 is less than or equal to x is strictly less than infinity, if f is non-increasing on close that one, open at infinity, and if integration 1 to infinity f of x dx converges, then limit x tends to infinity x into f of x is equals to 0. Okay. Now we'll see example on integral test. Discuss the convergence of the series. Example, discuss the convergence of the series n runs from 2 to infinity 1 upon n into log n raised to alpha, where alpha is greater than 0. Solution. Here f of n means 1 upon n into log n raised to alpha, where alpha is greater than 0. Therefore, f of x is equals to 1 upon x into log x raised to alpha, where alpha is greater than 0. Okay. See here students, as x into log x increases, 1 upon x into log x decreases. Means what? F be a non-increasing means decreasing function on interval close that to open at infinity. Okay. So therefore, by integral test for convergence of series summation n runs from 2 to infinity f of n converge and integration from 2 to infinity f of n, see here f of n or f of x dx converge or diverge together means what? If series f of x converges, then if integral f of x converges, then series f of x is convergent. If integral is divergent, then series f of n will divergent. Okay. So we will check convergence of integration 2 to infinity f of x dx. Integration from 2 to infinity f of x dx is equals to integration from 2 to infinity 1 upon x log x raised to alpha dx. Okay. This is nothing but limit s tends to infinity integration from 2 to s. Where is s 1 upon x log x raised to alpha dx. We solve this integration by substitution. Put log x is equals to t. So take derivative on both sides. We get derivative of log x is 1 upon x dx, which is equals to dt. Okay. Now if we put x is equals to 2, that implies t is equals to log 2. If we put x is equals to s, that implies t is equals to log s. Now put these values in this integration, we will get integration from 2 to infinity f of x dx is equals to integration from 2 to, here is log 2 log s. Okay. And this f becomes dt upon t raised to alpha, because log x is t, so it is t raised to alpha, and 1 upon x dx is dt. Okay. Now take integration. This is nothing but t raised to, this can be written as t raised to minus alpha, and integration of t raised to minus alpha is t raised to minus alpha plus 1 upon minus alpha plus 1, limits from log 2 to log s. Okay. So here 1 upon 1 minus alpha is constant, so take it outside. Here we will get log s. Actually this is limit s tends to infinity f of x dx is equals to limit s tends to infinity. Okay, here again limit s tends to infinity. Here is also limit s tends to infinity. Okay, 1 upon, this is log s raised to 1 minus alpha minus log 2 raised to 1 minus alpha. Now put limit. So integration from 2 to infinity f of x dx is equals to, this 1 upon 1 minus alpha is constant, if we put, see here students, this is equals to 0 minus log 2 raised to 1 minus alpha upon 1 minus alpha when alpha greater than 1, and which is equals to infinity when alpha is less than 1. Now question is arises, why this is? Because see here students, if alpha is greater than 1 here, if alpha is greater than 1 means what? If here alpha is suppose 2, so your this limit become limit s tends to infinity 1 upon 1 minus alpha into log s raised to 1 minus 2 is minus 1. Okay, so don't think about this. This is a constant, so it remains as it is. Limit s tends to infinity. So limit s tends to infinity 1 upon 1 minus alpha 1. This is raised to minus 1, so it is 1 upon log s, and as s tends to infinity, log s tends to infinity. So this is 1 upon infinity, this becomes 0. So remains only log 2 raised to 1 minus alpha upon 1 minus alpha. Now see what happened if alpha is less than 1. If we choose here alpha is less than 1, means what? Suppose here if we choose alpha is equals to 1 by 2, which is less than 1. So here we will get log s raised to 1 minus 1 by 2, means only 1 by 2. So as s tends to infinity, log s tends to infinity. So this total term becomes infinity, and if we subtract from infinity any number, we will get infinity. That's why we will get this integral is equals to infinity when alpha is strictly less than 1. Okay. Now we will check the convergence for alpha is equals to 1. When alpha is equals to 1, integration from 2 to infinity, this becomes dx upon x into log x raised to alpha is equals to, here alpha is equals to 1, so our integral becomes integration from 2 to infinity dx upon x into log x. Okay, so integration of this is log of x. Okay, integration from 2 to s. Okay, take here s. So this will become, if we put upper and lower limit, this will become log of log s minus log of log 2. Okay, as s tends to infinity, we will get this integral, this value is equals to infinity. Okay, so dx upon x into log x is equals to infinity. Okay, therefore see here this integral 2 to s dx upon x into log x converges if alpha is greater than 1 and diverges if alpha is less than or equal to 1. Therefore, integration from 2 to infinity dx x into log x raised to alpha is equals to infinity if alpha is less than or equal to 1. Okay. And integration from 2 to infinity dx upon x into log x raised to alpha is equals to minus log 2 raised to 1 minus alpha upon 1 minus alpha if alpha is greater than 1. Okay. Therefore by integral test for convergence of the series series n runs from 2 to infinity 1 upon n log n raised to alpha converges if alpha is greater than 1, because this integral converges if alpha greater than 1, and diverges if 0 is strictly less than alpha, which is less than or equal to 1. Okay, because this integral diverges if alpha is less than or equal to 1. Okay. Let us take next example. Discuss the convergence of the integral. Integration from minus infinity to 0 1 upon 1 plus x square dx. Okay. Solution. We solve it by definition of convergence of improper integral of first kind. Okay. Let f of x is equals to 1 upon 1 plus x square. Okay. 1 upon integral from minus s to 0 1 upon 1 plus x square dx. Okay. Solve it. This is a integration of tan inverse of x. Okay. Limits are from minus s to 0. Put upper limit and lower limit. We will get tan inverse of 0 minus tan inverse of minus s. Okay. This is nothing but tan inverse of 0 is 0 minus tan inverse of apply limit on both sides. Limit s tends to infinity. F of s is equal to limit s tends to infinity tan inverse of 0 minus tan inverse of minus s. Okay. Tan inverse of 0 is 0. Tan inverse of infinity is pi by 2. So we will get this pi by 2. Okay. Therefore, integral from minus infinity to 0 1 upon 1 plus x square dx converges. Okay. This converges. Okay. Students, write down one note. If f of x is Riemann integrable, on closed interval AB, then integration from minus infinity to infinity f of x dx is said to converge if integration from minus infinity to c f of x dx and integration from c to infinity f of x dx are both convergent and we define integration from minus infinity to infinity f of x dx is equals to integration from minus infinity to c f of x dx plus integration from c to infinity f of x dx, where c is any arbitrary real number, and the value of integral is independent of c. It is also noted that it is to be noted that f is not unbounded at any point of R. Okay. See here, students, it is very important note. If f of x is Riemann integrable on closed interval ab, if integration from minus infinity to f of x dx is said to converge if integration from minus infinity to c f of x dx and integration from c to infinity f of x dx are both convergent. Means here we have split interval minus infinity to infinity in two parts, minus infinity to c, c to infinity. We define integral from minus infinity to infinity f of x dx is equals to integral from minus infinity to c plus integral from c to infinity f of x dx, where c is arbitrary real number and the value of integral is independent of c. Means this value of integral does not depend on c. Here we can take c any arbitrary real number. Okay. It is to be noted that f is not unbounded at any point of R. This f is not unbounded at any point of R. Okay. Let us see example for better understanding. Example is test for convergence. Firstly, integration from minus infinity to infinity x raised to 1 by 3 dx, and second is integration from minus infinity to infinity dx upon 1 plus x square. Okay. See here, students, solution. Here, this integration from we have integral from minus infinity to infinity x raised to 1 by 3 dx can be written as integration from minus infinity to 0 x raised to 1 by 3 dx plus 0 to infinity x raised to 1 by 3 dx. Here you can take 1, 2, it doesn't matter. Okay, it is arbitrary number. Okay. Now we have to test the convergence of this integral. For that we have to test the convergence of these two integrals. If both these integrals are convergent, then this integral is convergent. If these two integrals are divergent, then this integral is divergent. Okay. So integral minus infinity to 0 x raised to 1 by 3 dx is, this integral can be written as minus infinity to 0 1 upon x raised to minus 1 by 3 dx. Now this integral is of the type 1 upon x raised to p. When p is less than 1, at that time this integral is divergent. So integral from minus infinity to 0 x raised to 1 by 3 dx is divergent. This is by p test. P test, p is equals to minus 1 by 3, which is less than 1. Similarly, integration from 0 to infinity x raised to 1 by 3 dx is also divergent. Okay, this is also divergent. Therefore, see here, both integrals on RHS are divergent. That's why integral on LHS is divergent. Therefore, integration from minus infinity to infinity x raised to 1 by 3 dx is divergent. Okay, very simple. Now solve second. We have integration from minus infinity to infinity dx upon 1 plus x square. This can be written as integration from minus infinity to 0 dx upon 1 plus x square plus integration from 0 to infinity dx upon 1 plus x square. Very simple. In value of this integration is pi by 2. We have, as previous, we have solved this example. Similarly, this is also pi by 2. So these both integrals are convergent. That's why this integral is convergent. This is homework for you. Solve this example. Okay. We will stop here. Thank you.